Hi class, we are now on 14.A. This is a pretty short lecture because we're going to expand more on in the further coming sections. So strongly acidic solutions can, let me make sure here. Strongly acidic solutions can dissolve lead. Weakly acidic solutions like buffalo wing sauce and Coca-Cola taste great during football season. Let me start that again. Weakly acidic solutions like buffalo wing sauce and Coca-Cola taste great during football season. What is the difference between the two? How can we measure the strength of acids and bases? Well, we're going to answer these questions. We must begin with pure water and the two species of the proton and hydroxide. Those define the acids and bases. So pure water always contains a small amount of hydronium ions and hydroxide ions. In its liquid form, water molecules constantly collide with each other. Once in a while, these collisions result in a transfer of a hydrogen ion from one molecule to another. That is, water molecules react to form hydronium ions and an hydroxide ion. This reaction is called the self-ionization reaction of water. For simplicity, we sometimes show this as a single water molecule breaking into two ions, which is what you see here on the bottom reaction. In pure water, one in every 560 million water molecules is ionized. The concentrations of hydronium ions and hydroxide ions in pure water are both equal to 1.0 times 10 to the negative 7. And we'll cover this more as we go on. Mathematically, we say in pure water, the concentration of protons or hydronium ions times the concentration of hydroxide ions is equal to 1.00 times 10 to the negative 14. So if this is 1.0 times 10 to the negative 7, and this is 1.0 times 10 to the negative 7, that's where the negative 14 comes from. So what happens if we add acid to pure water? Suddenly the concentration of protons jumps up. This excess proton reacts with a small amount of hydroxide ion that is present, and the concentration of hydroxide ion decreases. On the other hand, if we add a base, the opposite occurs. The hydroxide concentration jumps up and the proton concentration decreases. The concentrations of hydroxide and protons are like a seesaw. If one goes up, the other goes down. Interestingly, even if the concentration of the protons and the hydroxide ions change, the product of the two concentrations remains constant. For liquid water at 25 degrees Celsius, the concentrations of the protons and the hydroxide ion concentrations always equals 1.0 times 10 to the negative 14. So what they're trying to say is this is a set number based on these two. And if this one goes up, this one has to go down. If this one goes up, this has to go down. But this is always this value. It doesn't change. So it'll adjust to make sure that this value is always what's equal. So the concentration of the protons and the hydroxide ions expressed in scientific or in exponential notation. We're going to use these notations quite a bit in the coming sections, so a quick review might be helpful. Let's express a number such as 0.00214, which is in standard notation, to be in scientific notation. In scientific notation, we write it as 2.14 times 10 to the negative 3. Scientific notation uses a coefficient times a multiplier, which is always 10 raised to an exponent. In scientific notation, the multiplier is always 10 and the exponent is always an integer. In exponential notation, we write the same value as 10 to the negative 2.67 for our, In exponential notation, there is no coefficient, only a base, which will always be 10 for our purposes, raised to some exponent. In exponential notation, the exponent is not always an integer. Notice that the exponent is negative 3 in scientific notation and negative 2 in the exponential notation. the value of the exponent in exponential notation is always within 1 unit of properly written scientific notation. Remember that when multiplying exponents, we always add the exponents together. Mathematically, this is represented by the generic x with the superscript m, x with the superscript n, and then we add those together. For example, we can find the product of 5, we have a 5 and the 2 power, and 5 and the 7 power, and what we do is we add those together, which gives the 5 doesn't change, but now we have 9. To do this, we simply add the exponents together. When multiplying scientific notation, we multiply the coefficients and then add the exponents. For example, this is where we multiply this, and then we add these together. And that's where the negative 14 comes from. If you're wondering where this number is coming from, we're going to cover that later. So don't worry about it right now. Notice it's not really talking about where this came from. We're going to cover it in a while, but we have to cover a few things for you to understand why we're going to use this. This table shows the concentration of protons and hydroxide ions in solution ranging from strongly acidic to strongly basic. Notice that the product of protons, the concentration of protons and a concentration of hydroxide ions is always equal to 1 times 10 to the negative 14. At neutral point, the concentration for both species is negative 7. So you can see that for both of these. The concentration of hydroxide, a proton, is greater than this in acidic solutions, but less in basic solutions. So what it's saying is that if it's strongly acidic, this number here gets smaller and this number here gets larger. Why is that? Because remember, these are zeros in front of the number. So these have this many zeros in front of it, where this one has just a few. So this is a stronger concentration than what this is. And as we go the other way, these numbers get larger, which means they're weaker, and these numbers here get smaller, which means they're stronger concentrations. Because to have a strong base, you have a stronger concentration of hydroxide ions than you do of acidic, and vice versa for that one. Okay, so the concentration, let's look at an example. The concentration of protons in an aqueous solution is 1.0 times 10 to the negative 6. What is the concentration of hydroxide ions? Is the solution acidic or basic? So this is something to refer to, but let's take a look here. So by inspection, you recognize that the concentration of hydroxide ions must be, well, first let's look, we're going to use this equation here, right? So in order for this to equal that, then it must be something that should be close to 8, right? Because if this and this, these two are added together, then it equals 14. So I'm trying to refer to this right here, right? Okay, so in this example, we notice that the proton concentration is 1.0 times 10 to the negative 6, which is a larger amount than the neutral water, because this is 7, so it's somewhere right here, which means it's weakly acidic. So in this example, all right, so which is larger than neutral water. Remember, the water is with a negative 7. Therefore, the solution is acidic. So in this case, how do we set this up? So the whole point is to show you how to set it up. We plug in this number for the protons. We know that this is the total number that the proton concentration and hydroxide will have. And then we isolate the hydroxide, and that's going to give us our concentration for our hydroxide, which is 1.0 times 10 to the negative 8. It's not always going to be that easy, so don't always assume that you can just subtract. I would get into the habit of doing it this way, because things will start getting more complicated, and the sooner that you understand how to use this equation, the easier. And since it's less than negative 7, it's acidic. Okay, so let's look again. Acid and base, they both equal when they're balanced at 1 times 10 to the negative 14, but if we change one, then that means that one of the amounts has to go up or down based on what we did to the first one. Then here is a scale that, if you notice, it goes from 0 to 14. This means actually 0 is very strong. It's negative 14 has all these zeros in front of it. So there's a very, very small amount. and vice versa. 7, -7 and -7, this is neutral. If it's not -7, then it's either going to go this way or this way, and it's either going to be weakly acidic or